Good morning, everybody. Did that work for you? This is going to be one of the more technical presentations, probably, and I'm more interested in people understanding the concepts than in necessarily even getting through it all. So just interrupt with questions if you have them. I'll be trying to pay attention. It's actually about a lot more than just simulating the effect. It's kind of general discussions of groundwater development and surface water, groundwater development on the effects on springs and everything like that. And it's only on water quantity. This isn't discussing quality effects that can also occur. The first part of this is kind of a definition. There are two things about capture, which is the term we use in kind of discussing this. The one this presentation is discussing is this water budget context, where when you pump from the groundwater, you can either increase flow from a stream or decrease groundwater discharge to a stream or to a spring or to a lake or any of those, or even just areas of natural evapotranspiration where you might have some native vegetation that is reaching down and using the groundwater. How much you either increase that inflow or decrease that outflow is termed capture. There's another one, again, that isn't really discussed in here, is a capture area. That's actually like the flow paths that go to a well, and that's important in wellhead protection. You'll see that if you're looking at, wellhead protection, or this particular contaminant could move to this well. But again, that isn't going to be discussed here. This is all about the water budget. I've divided this into three areas. Kind of the source of water to wells, some misconceptions about capture, about groundwater and surface water interactions, and then the development and analysis of capture maps, which is what this diagram is. So the first source of water to wells is always the removal of water from storage. You have to induce flow to the well, and the only way that happens is to drop the water level at the well. And that can continue for a long time. This well is actually, this hydrograph is a USGS observation well down in Parowan Valley. Luckily in Lower Bear River this isn't happening, which is why I had to find another example for this slide. But so that's always the first thing. You remove water from storage. The second source of water to wells is capturing natural discharge. So capturing water in a river or a spring or an evapotranspiration area. So eventually you capture more and you dig less out of storage and your water levels kind of stabilize. On that previous hydrograph, the fact that they were not stabilizing means a few things. Number one, it's having a hard time reaching out to anywhere and capturing some discharge, or that the pumping exceeds natural discharge, which is what is happening in Parowan with that one, or that it's just a long ways to get to any connected surface water feature that it can capture. So the important thing to remember there is if there is nothing that can be captured, you're going to keep having drawdown at the well and surrounding the well, because the water is going to have to keep coming out of storage. The third source of water is actually you can increase recharge. That doesn't happen very often in most of our areas in Utah or throughout the West. Because for it to happen, you need a perennial stream in contact with the groundwater. So Salt Lake Valley, it can happen. Lower Bear, it can happen. A lot of our valleys, though, most of the recharge from the rivers is actually happening as they flow into the valley, and they are above the water table. So it's like this picture, where the river is coming in and it's leaking and it's recharging, but nothing you do down here will increase that leakage. If you're not connected, you can't increase the recharge from a stream. Capture cannot occur in either of these two. Obviously, if it's dry, which can also happen, a lot of our streams are only flowing in the spring for a little while or something, or we're diverting them all out for irrigation and things. As we said, drawdown continues until other discharge is reduced, and this is just an example of a spring. And the drawdown has to actually reach out to that spring. So the cone of depression has to just keep going until it actually affects the water level at that spring before it can be captured. Okay, there's a few common kind of misconceptions, and I'm getting that term from another paper. On some of these slides, you'll see a lot of things about leak and Barlow. There are a couple of USGS people who have done a lot of papers about capture, and they kind of came up with these misconceptions and why they are not true. So one of them is that total development of groundwater in an aquifer system is safe or sustainable at rates up to the average rate of recharge. And the diagram down here is actually of the lower Bear River area, kind of a schematic. We have mountain precipitation, and some of that contributes recharge. We have some springs that can come out along the mountain front. In that valley, a lot of evapotranspiration from groundwater, the two rivers, the Malad and the Bear. And a lot of fill drains in that area that were put in back in the 30s because they were so wet they couldn't farm effectively. And those drains then take that water out of the fields and move it to the rivers. But what you can see here is that if you actually pumped at the rate of all of the recharge going in, then you would not have groundwater discharge to the rivers or to the drains or to evapotranspiration. So safe and sustainable are more of regulatory decisions, not really a hydrologic term. You know, some regulator has to decide, well, we need to pump and we can tolerate a certain amount of less flow in a stream, or less flow at a spring. So those are all regulatory decisions, not necessarily really hydrologic decisions. Capture is not dependent on the rate or direction of water movement in the aquifer. So a lot of times in our Great Basin area, people will say, well, water is moving from one valley to another. And so if you're pumping, you know, in a certain place, then you won't affect that movement. And that's not necessarily true. It doesn't really matter if the well is below the stream. I can't hand draw contour, but if you were to draw down, it would still come back and hit that stream. It doesn't matter. So all of these, assuming that the aquifer properties are the same, the well would affect the stream in exactly the same way. And it doesn't matter, right, what that rate of flow is either. Oops. I seem to have missed one. Whoa, where did it go? I lost my thing. All I did is push the back arrow. What did I do here? Wow. I can't get back. It won't go backwards. I didn't mean to cause trouble. No, we were down farther than that. We were down that one. Wow. Huh.
Let's just do this really quick. This one?
Yeah, that one, if it will start. If we're happy now. Okay, thank you. This is kind of the same as the other one, except it also shows that a groundwater divide also doesn't really affect capture. The capture can reach across a groundwater divide. And this is important in a lot of our water rights are based on, well, surface water divides. which may or may not equal groundwater divides. They kind of do, typically in Utah because of the mounding under the mountain recharge block. But pumping can change that groundwater divide or completely remove the groundwater divide. So it's not a hydrologic barrier, it's just a water level. Again, the well would affect the streams, both streams exactly the same. Not stream 1 and 2, but stream 2 would be affected the same amount in each of these cases. The process of capture doesn't stop when pumping ceases. It can actually go on for years afterwards. There will be less volume in that river or in that spring for years after the pumping stops, depending on the aquifer properties. And this is important because a lot of times with new pumping, there'll be some kind of mitigation or monitoring, and they'll say, you know, well, if something starts happening, we'll stop, which is good, but you have to remember that things will still be affected even after that pumping stops. Okay, so confining layer might be a little technical here. A lot of our valleys will have some clay in them. Most of ours are kind of an intermix, so it's not a real thick layer like this picture, but let's say that it was. That won't necessarily stop the depletion. It could speed it up. It could slow it down. It could reach out and just capture something else if there's anything else to capture. So on the next slide, you kind of try to remember that the pumping is kind of closer to the river, and there's either clay beneath the river or clay along the margins or no clay at all in the next picture. So if there was, you know, no clay, hypothetically, you would get this kind of response of the stream flow depletion. If there's clay right beneath the river, then that will be slowed down. Eventually, if there is nothing else out there that this pumping could capture, it would eventually, 100% of the pumping would come, but it would take it a long time. It would come from the river. And again, in the meantime, you're just going to keep getting drawdown at that well and everywhere around that well. If there's clay along the margins, it could actually speed up the process of capturing the stream. And that's more just a fact of the storage coefficient. The drawdown happens faster in a confining layer, and therefore it will affect the stream faster if there isn't clay right under the river. Okay, Malad, Lower Bear River Study Area. So this is up in, I just said to show this, I bet. It's up there. It's that little red square up there. Great Salt Lake is sitting in here. It's part of the Great Basin Carbonate and Alluvial Aquifer System. Typical basin and range topology, flat basin, normal faults on both sides, high steep mountains. In that case, really steep. The Wellsvilles are kind of weird mountains. In that study area, the groundwater budget is about 200,000 acre-feet per year. And the reason I'm showing this is because when Division of Water Rights came to the USGS and wanted a way of estimating what new water development would do to the Malad River, we proposed using an existing model, the Great Basin model, refining it in the Lower Bear River area, calibrating it to determine aquifer properties, and then using that to help estimate the effects of development on the Malad River. That had another one, I guess not. This is the, so the zoomed in area. For those modeler type, if there's any out there. In the Great Basin model, this grid cell is 1 mile by 1 mile. In this one, it's a fifth of that, so just over 1,000 feet. So that the rivers could get separated. In the Great Basin model, these two rivers are actually in the same cell in places. It's important if you're going to think about simulating the effect of groundwater development on discharge to have all of the discharge in the model. And in this area, there's a lot of it. There's evapotranspiration areas. There's all those areas of fill drains. There's some natural spring areas that are kind of too big to be a point. They're just, you know, large areas where there's groundwater discharge. and the two rivers. The Bear is the one over here, and then the Malad. So this is the grid. And the first thing you have to do is say, well, what do we care about? And in this case, the water rights had told us they care about the Malad River and actually another area I'll show on the next slide. Kind of the combined. They were having some water rights issues with people who had existing water rights and were worried that they would be impacted. So this will all be talking about mod flow because that's what I used in this. I'm sure you could use other models too. But the main thing is you have to say, in the model, I can get this number out of that model. And in this case, it's the groundwater discharge to the Malad River. You can define more than one value that you want it to think about. So here I actually did, back on that last slide, most of those areas are defined as separate observations that I keep track of during this process so that different maps can be made, and I'll show that at the end. So everything that's happening in those red cells is part of what the state wanted when they came to us. And the ones down here are because of all those filled drains, they're actually draining to the Malad River. But if you were to drop water levels below those and they were no longer contributing water to the Malad River, then the Malad River would have less water. So this process of the capture map, to make that pretty picture that was at the beginning, first you have your calibrated model, and you see what it does for that one little part that you care about. And then you add a well in one cell, you run the model, you calculate the difference in the simulated value, keep track of all of that, save that percent, and it's percent of the well withdrawal, so it's not percent of the river. So that way you kind of can kind of say if it was 100 acre feet being withdrawn, then 82 feet of that, acre feet of that came from the Malad River. If it was 1,000, then 820 came from the Malad River. The real world is not perfectly linear, but it works fairly closely. You put the well at another place in the model, and it's going to be a lower number. It's 26%, for instance, in that cell. And you do that several hundred times. And either every model cell or enough that you feel pretty good that you can get a good interpolation. In this case, I think it was like 2,400 cells. It took it about 200 hours to run. And then at the end of all that, you can process it all using GIS or some other method and get these maps. And what this then, it gives a way for water managers to be able to look at a point and say, okay, if someone puts a well here, 80% of that water will eventually come from having less water in the Malad River. And this is all an eventual, it's a steady state model, long-term effect. So we're not talking about storage in this model at all. It's just the long-term, where is that water going to come from? Some things to notice is that, there are areas, so in general it makes sense. The closer you are to the river, the more you will capture the river. Right up here, there's an area where it doesn't seem to. It's because there's actually some evapotranspiration that it's slowing down instead. Another spot right in here where it doesn't seem to be capturing the river is it's capturing a spring instead. Down here, where it seems like as you move farther away from the river, you're still capturing a lot, is because of all those filled drains. So it is stopping the discharge to those filled drains and affecting the river. Okay, so then you can say, okay, well, 50%. I don't think it's quite 50. I have a number here, but we won't worry about it in particular. About 50% of water in that well then would come from declining flow in the Malad River, which hopefully kind of makes you think, well, where did the rest come from? And, okay, I better find my numbers so I can make sure I get to 100 here. Or close to it, at least. Actually, it was 42% of that other dot on the Malad River. In this particular case, there'd be 36% of the water would come from reducing flow to springs. Any spring, the way I set this up, but it would basically be the ones, closest to it. And 10% by reducing, even at this well, 10% of it would come from reducing groundwater discharge to the Bear River. Obviously, if you're near the Bear River, you will capture the Bear River a lot more than the Malad River. So the important thing to remember, and that actually only adds up to 88 because 12% is from little things I didn't calculate like the other ET areas, or because this was part of a big model, it can actually reach out to the other valleys and slow down a little bit of discharge in those valleys also on each side. Kind of going back to that slide that showed the clay layers. In this valley, the USGS kind of thinks that there aren't really well-defined clay layers, but there are definitely clay layers, little lenses and thinner layers. And in the model, there's no simulated thick clay layer, but there's something called vertical anisotropy. And in the model, it's about 70 times more permeable horizontally than vertically, or more conductive horizontally than vertically. And the effect of that is that if you put it in, so all those other maps are with the well in layer 2, which is kind of where most of the wells that are already up there are. If you put it deeper, it's actually interesting because you would get, so oops, sorry. Oh man, backward is tough, there we go. So if you put the well deeper right under the river, you would get less effect right on the Malad River. But if you put the well deeper under the Bear River, you would actually get more effect on the Malad River. And that's a matter of, like I said, if you have that anisotropy, it reaches out and then finds a way to reach up. And so the vertical complexity is can be pretty complicated. And in a lot of our models, we don't know that number that well because we don't have a lot of vertical water level data and things. So it's kind of one of our harder numbers. But just to acknowledge that it exists is a good thing. So in summary, we talked about the source of water to wells always affects storage and eventually affects something else. And that however much you take out of a well is eventually going to not come out of somewhere else. It might take it a while, but it will stop discharge somewhere by the same amount that you took out of the well. Kind of some of the misconceptions about capture, the rate and direction of groundwater flow doesn't matter. And that's kind of the main one that is really important. And then the development and analysis of these capture maps, and these can be done for anywhere there's a model that exists. You can do this. And I have examples on my poster out there from Snake Valley, where Melissa Mossbrook in our office did the same thing for some springs in Snake Valley using a different model. So it's kind of a good way of showing what could happen. So are there any questions? And just a couple of our reports. Yes?
Hi, this is fun stuff. I was wondering if you could just give a little more information on how you calculated ET and at what scale that was compared to the scale of your model.
Oh boy. We did ET. The scale, we use land use maps like from NLCD. And I don't even remember what that means now. But and then looked at kind of consumptive use of those versus how much precipitation was going on. So consumptive use of the vegetation that was there versus how much precipitation might be coming on. And then if there was no other source of water, assumed that they were getting what they needed from groundwater. But the scale was actually probably finer than the model grid for those. So and that's for the ET from groundwater. I didn't calculate ET that's from precipitation. That was already included in the recharge number we got from there's other people in the USGS who do a method called basin characterization method, where they've already accounted for all of that, and they give us here's what's left, here's your recharge number. So, and that he does at 270 meter scale or maybe 30 meter scale. I can't even remember. It's pretty fine. Any other questions? Thank you.